you may have seen some of this stuff before, but a lot of this is going to be brand new. So we don't really care about protons and neutrons. They're just not that important because we want to get to chemical reactions. We want to get to why things do what they do. And that is an awful lot to do with the electrons. Where are they? Where are they kept? How do they behave? And those kinds of things. So that's the purpose of this podcast, right? So when you see a light bulb, something glowing like that, this is what's happening. Energy is being absorbed by an electron. That electron jumps from one energy level to another, so the first to the second, or the first to the eighth, or the second to the sixth, and then it looks around, and none of its electron friends are there, and it gets sad, and it jumps back. And since it was at a low energy level to start with and absorbed energy to jump up, then of course when it falls back down it has to release energy. It releases energy in the form of light. Could be ultraviolet, could be visible, could be infrared, could be lots of things. The ground state is where it starts out at. The excited state is where it jumps up to, and then it returns back to the ground state. Every element and compound has its own unique signature, and we call that signature an emission spectrum. Nothing will have an emission spectrum just like hydrogen, not even water, because once you mix the hydrogen with the oxygen, it's going to be slightly different. So we can take the light that comes from a sample of hydrogen, say, and pass it through a prism, something that splits the light into its bands of colors, and we can get an emission spectrum, or all the colors produced. As you can tell, this is the colors that are given off by hydrogen. Look, you got a couple purples, a blue, a teal, and a red, and that's what you kind of got going on here. But what you guys need to realize is there are some colors you're not seeing. This right here. Now, they didn't fall very far. And when they don't fall very far, that's not as much energy. And so light that doesn't have much energy is what we call IR, or infrared, below red. That's what that means. Meanwhile, the ones that fell a great distance like this, these emit a lot of energy, and that's called UV. So even though in this right here, you're seeing those colors with the naked eye, if you have better equipment, you can actually detect other beams of light given off as well. You've already seen hydrogen. Here's a couple more. There's Hg, which is mercury, and Ne, which is neon. And you can tell many of the colors are similar, but none of the signatures match up exactly the same. And we can measure the wavelength of the light, and you can see a scale at the bottom, starting with 400 nanometers for the wavelength of light, going up all the way to 700 or 800 nanometers. So we can measure its wavelength of the light correlates to a color. It has something to do with the color. Way back when, people thought, light is light. But then as we became more and more knowledgeable, this is the early 1900s, people started to have an argument. Is light a particle or is it a wave? We know things occur in waves, like waves of water, sound waves. But sound waves don't behave like particles. And water waves don't behave like particles. They go up and down like a regular wave. Turns out that light has what we call a dual nature. That dual nature means that it behaves sometimes like a particle and sometimes like a wave. So let me explain real quick what I mean. The photoelectric effect is what happens when you shine light on certain metals. It knocks electrons right off of it. And when that electron goes flying off, it travels in a wire, and that's called photo, meaning light, electricity, the photoelectric effect. Not all light will do it. You can take a lot of infrared light, like heat, and you can take that infrared light and you can shine it on a solar calculator all day long. You can get 15 people all aiming their body heat at the calculator. Nothing will happen because the photoelectric effect says light has to have a certain amount of energy before it will knock loose that electron. And the energy has to be in discrete amounts, meaning not somewhere between 1 and 2, but 1 or 2 or 3 or 4 or 5. There are discrete steps, not anywhere between 1 and 2, anywhere between 2 and 3, because anywhere between 1 and 2 could almost be infinite, right? You could have an infinite number of settings in between 1 and 2. So the photoelectric effect said that light has to have a discrete 1 or 2 or 3 or 4 amount of energy to knock loose an electron. I can do the same thing for you. Take the pencil that's in your hand, hold it up, get one of your family members to throw something at it. Start light. Start a cotton ball. Throw 2 cotton balls at it. 15 cotton balls at it. It's not going to knock that pencil loose. Pick up something heavy like your family car. Now throw that at the pencil. Is it going to knock it loose? Sure. Get a big rock. Throw it at it. Is it going to knock it loose? Sure. But a rock doesn't weigh as much as the car. The point is there's a boundary level at which you knock loose an electron. And that taught people that, oh, light behaves like a particle. They behave like waves because of something called diffraction and interference. Diffraction is when light bends, just like beams of electrons bend. Interference is where you have a positive effect on a wave, meaning, let's draw a wave. Let's talk about wave interference. So here's a wave, and if I throw in another wave that is directly opposite it, the top of one wave meets the bottom of another, then those waves cancel each other out. The resulting wave doesn't even go up at all. This is what noise canceling headphones do. They actually take the wave coming in, there's a little microphone. The noise canceling headphones produce a wave totally opposite to it, and so when the sound waves run into each other, they cancel each other out. Let's do a wave that shows not negative interference, because that's what that is. Let's show a wave that does positive interference. And this time, let's say that the wave doesn't quite go as high, but it still matches up. But this time, instead of the high point meeting the low point, the high point of one wave matches the high point of another wave. So what does the resulting wave look like? Well, the resulting wave actually adds together. Here is the resulting wave. The resulting wave goes way up here, and then way down here, and then way up there, and then way down here. And we call that positive interference because the waves add together. Light can do that. Beams of electron can do that. And so we say that light and electrons both have this dual nature because they behave as both particles and waves. These people helped us understand the ideas behind light. Bohr was very instrumental in talking about where do electrons live. The Bohr model was the one, and I'm sure you guys have seen this, the Bohr model was the one where it said, here's the nucleus, and then you've got electrons out here, and that's the first energy level, and this is the second energy level. First one holds 2, second one holds 8, third one holds 18, and so on like that. That was Bohr's model.